Yo, what's up, everyone? Welcome back from break. I feel like it's been a long time since I made one of these videos, and every time I take a break, I'm like worried I'm gonna forget how to teach when I come back. Um, but anyway, I hope you had a nice break. I really had a great break myself. Really relaxing. Mental health has been trending upwards for a while, which is really nice, and I hope the same for you. So I'm going to announce all the end of semester stuff, but the basic gist is we're not going to do anything different. Um, we're just going to continue on in the next 2 weeks with 2 more weeks of lessons. And one reason is most people are behind at least the probability test. Like last time I checked, only like a third of you had done it. So a lot of you still have some catch up work to do. And then secondly, we're a little behind on content. Not too behind. I think we're doing amazingly well considering it's like literally just 2 times a week I get to talk to you. Um, and we're going to be fine for the AP. But if we had taken these 2 weeks to just do a review, I don't know how much we'd gain from that. And it would set us back 2 more weeks. So, yeah, all that is to say, we're looking at stuff that is pretty similar to stuff we've done in the past. This is like part two of probability. Let me just write that so we understand what's going on mentally. Where we had our probability test before, and this is the second probability test we'll have. We'll do another month of probability work. And in this month, our goal is going to be to combine everything we've learned about probability with stuff from the beginning of the year. And then we're going to start our big push towards the end of the year. So really the end of the year, the last 2 or 3 months is all like the same concept. But we have to get there first. So we're doing probability for a bit longer. Hopefully all that made sense. I was just kind of rambling. Maybe I did forget how to teach. But yeah, okay. So, so we're going to start by looking at some distributions in a very similar way to what we did before. But then we're going to push it to everything we know about this class, which is center, shape, and spread. So first, there are some definitions in the front, and this is really helpful for the way we frame this, because in my opinion, this whole set isn't very difficult, um, but you have to make sure you're understanding it in the right way. So before it even tells us any questions, it says a random variable is any variable whose outcome is decided by a chance process. A probability distribution of a random variable gives the possible outcomes and their probabilities. And there are three types of random variables: categorical, discrete, and continuous. So all of that is to say, we've seen probability distributions before, but whenever we see a probability distribution, we just have to think that it's measuring a random variable, right? So for the second one, for example, we know that we're using a random number generator for numbers 1 through 8, and the number that we get is a random number that's variable because it depends on what we choose. Okay, so we call all of this random variables, but I also just like to call it probability distributions, and they're pretty much the same thing. And all we're going to do to start this is extend the categorical versus quantitative stuff that we did earlier in the year and split quantitative into what's called discrete and continuous. So these are kind of two big vocabulary words. Um, and we have these three distributions here. The first one is candies out of a bag, something we've seen before. A random number generator, something we've seen before. And then the last one we haven't exactly seen, but it looks similar to like a table we would have seen in the beginning of the year. This is just the weight of a randomly selected goat from a farm. Okay. And it's first asking us what type of probability distribution each of these are. And hopefully we can see that all three of them are obviously different. And the first one we already know is categorical data, right? And the key to this is what we're trying to find is what type of candy it is. Probabilities are always going to be decimals or percents or fractions, right? But whatever type of data, or in this case, possible outcome, those are going to indicate whether it's categorical or quantitative, right? So the random variable here is what type of candy you select, right? And the type of candy is a category, not a number. So the random variable is categorical, okay? So you're always looking to see what are the possible outcomes. We're not talking about data, we're talking about possible outcomes. So the possible outcomes here are categorical. now we're going to look at the second two, and this is completely new stuff. And it's the difference between discrete and continuous. And I think that this is pretty easy once you get the mental click in your head. So if we're looking at this first one, we're trying to find the different probabilities when we select a number with a random number generator. So like you guys have probably seen the random number generator. It's looking really bad right now. That's fine. You could Google random number generator and you click generate and it's going to give a random number 1 through 8, right? So a random number 1 through 8 means that the possible outcomes are fixed, right? There's only 8 possible outcomes in this instance. So a discrete, like we're pretty much just trying to figure out the difference between these two things, discrete and continuous. And some of you might already figure out that. So all we're trying to do is distinguish between discrete and continuous. And this might be kind of clear to people just by looking at them. But a discrete random variable or a discrete probability distribution has fixed outcomes, right? You're either 1, 2, 3, 4, 5, 6, 7, or 8. They are numbers, so it's not categorical, but this is discrete. And the reason is you can't be anything but one of these 8. There's a finite number of possible outcomes. The alternative would be if you could do something like 1.5. A kind of helpful way to think about it is like decimals and stuff like that. And so far, I think I haven't explained it that well, and that's fine. This is the most important part of the first page. Here, all it's telling us is that we're going to randomly select a goat from a farm. And we know that each of these intervals has a 20% chance of occurring, right? This isn't saying that 20% of the goats weigh 150 pounds. It's saying that 20% of the goats are in this interval. And if we're trying to think of what are possible outcomes here, think that a weight could be any number, including any decimal to like a really far number, right? So if the weight was like 220, that's a possible outcome. But 220.1 is actually also possible. You could weigh yourself and see that. If you used a super, super, super fancy scale, you could find your weight to a infinitely small decimal, right? So now I think this should make sense, right? This is going to be called a continuous distribution. And it's called continuous because data can be anything from, in this case, 150 to 275, any number in between them, any infinitely small decimal number too. A discrete probability distribution has finite outcomes, right? You can't be in between them. There's no 1.5. There's definitely no 1.1. But if there's infinite possible outcomes, which is something that happens a lot with stuff like weight, height, time, that kind of thing, that's going to be continuous. And what's important to realize is that that's going to affect our graph as well, right? So part B of this is we're going to graph all of them just to see what they would look like. And this is kind of just a review of a lot of stuff we've done this year. So we'll start with categorical, then we'll do discrete, and then we'll do the continuous. But hopefully everyone sees the big difference between the two of them and how to frame it in your mind. If we have a categorical data set, remember that we split the bars up and we don't connect them, indicating that they're separate from each other, right? So in this case, it gave us fractions, but if we wanted to draw them, we should put it in the decimal. And it's pretty easy in this case. The largest one is 35 and the smallest is 10, but we should go up by like 5s, 5, 10, 15, 20, 25, 30, 35. And then we go up by each of these. So the Kit Kat was 10. Okay, so that's my first graph. This looks just like stuff we did in the beginning of the year. And categorical, you split them up because we know that they can actually be in any order, right? On a typical graph, like the ones we're going to see in the next two, we know we go from 0 to whatever the highest x value is, but there are no x values here, right? So each of these is interchangeable. And that means that we can't find a center, which is what we're kind of building towards. For 2, it's our discrete random variable, and it's everything from 1 to 8, and they all have the same chance, which is 12.5%. So I'm going to draw the scales in first. And here there's only one probability, 0.125. So every single bar is going to be that tall, but it's actually going to make drawing this really easy. And I'm going fast because once we draw them, the explanation goes from there. But that's what this probability distribution would look like. All right, 1 has a 12% chance, 2 has a 12% chance, 3 has a 12% chance, etc. The final one is continuous, and it's actually going to look pretty similar to the one we just drew. We know that we have 5 bars, and each of them is 0.2. But instead of each bar being a single number, each bar is an interval, okay? So I'm going to draw that in, and this is something that's really important. Okay, so I have my numbers on the bottom, but what makes this so different is that each of the bars I draw has to show an interval and not a single number, okay? So there's nothing from 0 to 150. We could even draw a little break there. But from 150 to 175 is 20% of my data. So if you have continuous data, your bars, and this is just like what we did in the beginning of the year, go in between the numbers, right? This bar indicates that 20% of the data is in between 150 and 175. And we keep going like that. And what's so different about that compared to the first one is that the first one, each bar has a specific number, right? So our discrete outcomes are listed on the bottom and their bar goes up, but a continuous would have the intervals on the bottom and then the data is in between them. So I think that's really, really cool and helpful to know. And hopefully you find that interesting and understand the difference, because both of these just kind of show up in life all the time. So know that if you see something like this, that is going to indicate a discrete variable, and something like this would indicate a continuous variable. Now that we have that, we're going to finally get into the actual math here. And that's going to be talking about the center shape and spread. So we have probability distributions, and we've talked about their shape, or at least how they look visually, right? But we know that there's 2 other big things for a distribution. Anytime we have data, anytime we have a graph, like a two-way table graph. So what we want to try to do is figure out which of these graphs we could find the mean and the standard deviation of, and which of them we couldn't find. So if I'm looking at this, we're going to come into similar problems we had in the beginning of the year. Categorical data, you can never find the center of, right? Because the data are interchangeable, and usually a mean can become a decimal because it's in between 2 values. But how can you say something's like Reese's Cup 0.5? You know what I'm saying? Does that make sense? There's no way. So categorical data, you can never find the mean and the standard deviation of. But if we're looking at these 2 distributions, and we'll look at the graph as the data as well, which of them is a mean possible, and which of them is a mean not possible? Just like with histograms in the beginning of the year, if you have intervals, you can't find the mean because we don't know exactly where this 20% of data is, right? So with continuous data or a continuous probability set, it's going to be impossible to find the center, right? Because we don't know where this 20% is within here. However, if you have a discrete random variable or a discrete probability distribution, you can always find the center of it, okay? And we're going to talk about the formula here, but hopefully everyone understands that. You can't find the center of this. You can't find the center of this, although it's probably like around here. But if you have this, a discrete random variable, you can find the center of it using kind of the formula we're about to do. Okay, so we want to figure out how we can find the center of the distribution, and I'm just going to give you the formula and we'll go from there. But all you have to do, and what we're going to call it is the expected value, is multiply every number to its probability. It's really, really simple. So let me do that, and then we'll talk about kind of why that works. But all you're going to do, and it's a little tedious if it's a lot of them, is you multiply the number to its probability. And we get 4.5. And the video went a little longer than expected. I kind of forgot. I literally did forget how to teach. So I'm going to skip the last part of this that I was going to do, and we're going to extend this to 2 lessons. But we want to talk about what this formula does and why it works. Okay, so if we're looking at this distribution, if I ask you to find the mean, think that the mean is what is the average roll you get from the random number generator. So we know that all of our outcomes have the same probability, right, of 12%. But we want to know what is a typical roll. So if you multiply every number to its percent, that's going to weight it, or be what's called a weighted average. Okay, so the expected value here, or the mean of this discrete random probability, is the weighted average. Okay, so all you're going to do is multiply the numbers to their percents, and that's going to be how you solve that. Okay. We're going to skip standard deviation because it's a little tedious, and we all just kind of need to get back in the swing of things. But really, really good work. I appreciate you.